All right, everyone, welcome to the last talk today in the applications track for Spark Summit Europe 2015. It's my honor to introduce Natalino Busa. He's a data platform architect at ING Retail. Please welcome him with a big hand.
Thank you everybody. It's really an honor and a pleasure to be here. So my name is Natalino Busa. I'm a data architect at ING Retail. My specialties are in the area of distributed computing and machine learning and big and fast data solutions. I would like to spend a few words about ING. ING Group offers financial services in a pretty large, to a large community of up to more than 30 million people. As well as small companies, big corporates, and all sorts of SMEs in more than 40 different countries. And in total, it counts up to a bit more than 50,000 people working in it. So one of the mottos and the missions of ING is actually to empower people to stay a step ahead in life and business. And one way to achieve that is actually to present 4 principles which are applicable to all the services and the products of at ING. So services must be clear and easy to understand. They should have a clear language. They should be easy to use. Also, they should be available anytime and anywhere. And we understand that the best decisions are informed decisions. Therefore, let's say we would have up-to-date, relevant information available for the customers in order to have the best possible information in order to take decisions both today as in the future. And of course, keep getting better. And that applies to the service themselves, but also to the infrastructure, the technology, and so forth. Now, it happens actually that these principles are quite applicable if you translate them into the data domain. So if you would make them, let's say, data principles, one way to look at those would be, of course, we need an architecture which is lean, easy to integrate, easy to manage and to control. The data should be available, consistent, streaming, and real-time and up-to-date. And empowering would translate pretty much into having all sorts of algorithms and analysis and real-time predictive analytics applied to the data, both as an event-driven solution as well as exposed via APIs to be consumed by a large set of, let's say, devices and channels. And of course, getting better, so being resilient, distributed, scalable, and maintainable. So within this context, actually, we see that at ING we deal with several sorts of data. Definitely, we do have big data as, let's say, the bulk of all the information available, which spans across several years. And if you consider on the vertical axis things like transactions or customers or sessions, you would see that if you would slice it horizontally, you would actually have a large amount of individual stories or timelines which would tell a lot about how a particular customer or accounts or session is developing over time. This is a perfect candidate, for instance, for an event streaming scenario in terms of data processing. And also you would have recent data. Recent data is actually not that bulk in terms of amount, but definitely extremely valuable. So to summarize, why fast data? Well, we need fast data because it provides us relevant, up-to-date information, and that's actually where we can deliver actionable events and actionable insights. And we do need big data because that's where we analyze and model the totality of the information available. That's how we actually can learn, cluster, categorize, and organize facts. So these two things actually, they come together, and it's really great to be here at Spark Summit because Spark is one of those, let's say, technologies that actually is bringing, let's say, fast data and big data together, or at least closer to each other. So one way to deal with this sort of architecture is, for instance, to start analyzing the available data. We would have, of course, data which are still available in file formats or in, let's say, what we call batched data. Files, database extracts, data sources which are available. And lately, we have other sorts of data which are more streaming in nature, so things about real-time APIs or events coming from all sorts of systems. The very first thing that you could do, actually, is to use Cassandra or a NoSQL solution and actually start collecting this information and, for instance, exposing on the other side by means of a number of APIs. Next, and we've seen that, for instance, in the keynote of today, one way to go is actually to have fast analytics running on top of this NoSQL substrate and provide data modeling on the data. So on one side, raw data, or let's say incoming events. On the other side, a platform like Spark, which actually creates and analyzes the data and creates the models and expose the models back, again in Cassandra, where Cassandra actually becomes the repository of for both the raw events as well as the model being generated. And since some of those events needs to be processed in matters of milliseconds, we do have, next to the fast analytics, also another track, which is actually provided by Akka in our solution. And it's actually an event processing pipeline. The event processing pipelines actually covers where Spark could not go in terms of speed. So all the scenarios which are from a single event down to, let's say, hundreds of milliseconds, where you need to perform your actions with a limited time budget in terms of latency, those are handled with event processing in Akka. So, in fact, this combination of technologies is actually quite good, and there has been a number of talks in the past, and still there are, about Cassandra, Akka, and Spark as being a good, let's say, recipe in general for machine learning, where you can actually take the Akka part and exploit the fact that you have a very fast reactive pipeline, combining with Spark, where you can provide ad hoc analytics and all sorts of machine learning, and use, in this case in particular, Cassandra as a sort of a layer to message back and forth between these two layers. So if we would zoom in a bit on how this architecture would look like, you would have, let's say, Spark being, let's say, the core for a data operating system or a data platform, where on top you would have all sorts of, let's say, specialized libraries and solutions for your domain. Think of SQL analytics, but also machine learning, or if you want, also graph-oriented algorithms and streaming. Well, the good part of it is actually to combine all this and having a common programming language or a set of programming language which can actually run quite nicely in the same framework. And once that you have this sort of connecting APIs, in this case with Cassandra, the main job becomes extract the data, create the models, enrich, transform the data, store it back to Cassandra, while on the bottom part you would have accessing the model, loading it up in the pipeline, and persist the state of the actor if required in order to have a resilient event processing pipeline. So if you would summarize in a few words, you could say that Cassandra is there to store all data, and Spark is there to analyze all data. And actually, if you put that together, it's quite interesting because Cassandra is a scenario where you have actually multiple rings where you could distribute across a number of, let's say, data centers or racks. And Spark actually, in a way, behaves as a sort of an overlay, which we could consider almost as a sort of, let's say, a virtual, let's say, ring, which is not meant for storing the data in a permanent way, but actually to analyze and operate algorithms and analysis on top of this data. So much for technology. I would like to spend some time now on the algorithms and how we kind of work with this sort of system when it comes to anomaly detection. So let's say that one definition that fits pretty well anomaly detection is an observation of a number of observations which actually is so different from the rest that actually almost implies a different mechanism behind as a generator for that mechanism. It's a very abstract one, but it's a good one because it covers lots of different classes of anomalies. Anomalies can be point anomalies, but could be also clustered anomalies of events which belong to a different collection of, let's say, of operation of transactions or events which do not conform to the rest of the events being seen. So in particular today I'm going to take two examples. One is going to be, I'm going to apply, let's say, a distance-based clustering algorithm, while the other one is going to be density-based. And the reason for taking these two examples for the anomaly detection is that actually they're quite representative for two different classes of activities or machine learning algorithms that you can run with Spark. In order to make let's say, this presentation and also the example more accessible, I've taken a public data set, which is the one available from Gowalla, and shows the number of a number of check-ins which are produced by a number of users for location-based social networks. Actually, Gowalla doesn't exist anymore. Was acquired a while back by Facebook. But the data set is actually kind of interesting because it's very down to the point. You would have a user ID, you would have a venue ID, latitude, longitude, and a timestamp. So what can you do with that? Well, let's start first by analyzing clustering of venues. The idea behind clustering venues is actually that the intuition that some venues, they have a particular pattern during the week, and they actually tend to stick to that pattern, while other venues, they might have a complete different pattern. So just have a look at weekly patterns for the city of New York. So what you could see is, for instance, that Madison Square and the Apple Store, they're quite popular on Thursdays. So for those sort of, let's say, venues, would make sense to have, let's say, a pattern that peaks on Thursdays. While, for instance, Statue of Liberty and Columbus Circle, they appear to be not popular on Wednesdays. So that's another fact that you could exploit. Now, if you would take this information, if you consider that the day of the week would constitute a sort of a feature in your in an histogram, so that basically your histogram and the components of your histogram are actually the elements of a vector of length 7. You can, in fact, already there see how easy it would be to transform that into a clustering algorithm for Spark. So let's consider vectors of 7 dimensions, 1 per day. And let's see whether we can find, let's say, clustering based on k-means, where the distance between those vectors are minimized. Now, if you have played a bit with machine learning, you will probably know that the first try is always actually delivers horrible results. So that's also in this case. Why? Because if you would compare, let's say, the vectors of the day of the week, and there is one venue which is popular on Wednesdays and whether it is popular on Thursdays, they will have distance 1, which doesn't make much sense since, in fact, they're two very different patterns. So one thing that you could do is you could start featureize or transform this vector into another space. And in this particular case, I've taken DCT, so the discrete cosine transform, as a way to go from the, let's say, the days of the week to another space, in this case, the space of cosine transforms. How would it look like? Well, you would have, you would take those check-ins, you would vectorize time, so you would transform the time variable into a vector of 7 fields, 7 dimensions, reduced by key, which I believe to be one of the best ever API calls of Spark. Actually, what would do is would sum up all these vectors and come up with an histogram, just there with simply writing underscore plus underscore. And after that, you could featureize those histograms. So go from the day of the week domain to the discrete cosine domain. Then I would say that the MLlib does the job. So you would call k-means and find clusters where the distance is the distance of patterns that have similar, let's say, waves during the week. You could see that in that way. And pretty much you're done. So what you could do with it is you could use for classification. So you could say, you could take a venue that you don't know and say, okay, how is this venue could be classified in one of my available clusters. Or you could use it for anomaly detection. That would be an anomaly detection based on a weekly pattern. And if at a certain point, 1 week, you would notice that the venue would have a completely different, let's say, look, well, that could be an hint to start an action. And the action could actually be an alert, but it could also be going in a different direction. Could be going in the direction of a marketing proposition or a security analysis. And of course, as you can imagine, you could do the same exercise for different domains. You could take operational excellence of your data center marketing data, events for anti-fraud or cybersecurity, and you could have there again similar interesting results. The second one, and the last one, which I want to present you, is clustering user venues. This takes a different approach. In this case, you will not have just a bunch of venues behaving in similar ways. You would have millions and millions of customers or users checking in various places. So what you would see is now that you would have things like localization of events for a given user. For instance, in this case, I'm taking an example again from the Goal dataset of a certain user that spent some time in Florida and some time close to South Carolina and so forth. And you could imagine that there is a combination of domain knowledge and algorithms, domain knowledge and machine learning. You would have rules that would say, okay, if the cluster is bigger than 10 events, you might consider that anomalous or not, depending whether is far away from where it's normally hanging or hanging out or not. And all these combination of machine learning and rules would actually determine the quality of your algorithms. So for this exercise, let's just ignore for the moment the rule-based, let's say, layer, which would be on top if you would do a real, let's say, full-fledged analysis, and let's focus on the clustering. Well, in this case, if you would take, let's say, k-means, you would have actually not that good results. And one way to get good results out of this sort of patterns is to use density as a way of clustering your data. DBscan is, for instance, is a very well-known algorithm that will actually look at the distances of your points and will try to cluster together points which are close to each other. And one nice feature of these clustering algorithms is that it doesn't create spherical clusters. So it can really shape according to the data available and the behavior of the user visiting several locations. So in this case, you would see that the trick here is not to have a massive algorithm applied to, let's say, the entire totality of events, but actually to parallelize and distribute the very same algorithm and apply over and over again for each user of your data set. Well, again, I think that that's a nice feature of Spark. You could actually fit this paradigm as well in Spark by saying that you would collect all the points related to a single user, and then once that the points are nicely organized in an array, run the DBscan algorithm on those arrays, one per user. And that is actually summarized by just writing DBscan underscore. So in a way, summarizing, we would see that clustering algorithms and to find anomalies in this case could be two different classes. One which actually is about taking big amount of data and applying clustering in a way that you would create maybe a smaller set of clusters, but taking all the data into account, or applying independently clustering all over and over on millions of data sets of limited size. Those would be basically non-scalable, let's say, application of clustering, while the first one would be a scalable one. Point being is that probably when you're doing machine learning algorithm with Spark, you might end up actually using them both. And they both have their place in in the pipeline of your system. So is one better than the other, and we should have all algorithms parallelizable or not? Well, actually, I think that choice is a good thing there. You would have a number of algorithms which are available in MLlib, and those will be the ones which are actually meant to be parallelized across a number of nodes to deal with the millions of samples. And you would have another set which might not be parallelizable, but very much, let's say, relevant in order to fill in the gaps and maybe apply algorithms which are not yet available in the libraries of MLlib. And there again, I think that the integration with R and Python is great when it comes to provide you a larger set actually of techniques to use in your machine learning pipeline. So to summarize, fast analytics, distributed data store, and event processing. I would like to spend a few words on the event processing part. When it boils down that you really need to go down to the millisecond, actually the event processing done with system like Akka based on an actor paradigm where the processing is triggered event by event becomes actually important. You cannot do, let's say, low latency analysis if that is not in the picture as well, at least if you want to reach the millisecond level. And is that always required? Well, no, it's not always required. So you could start by considering the following. If your training and your scoring are all in the range of minutes or seconds, Spark, I think it's a good option. You would actually cover the entire pipeline just using Spark. When it comes down that you might want to combine, for instance, training in minutes or seconds and scoring in milliseconds, then I would say that the Spark-Akka combination is a recipe that you might want to try. So for that part, actually, we build our little shell on top of Akka, which is what we call the Quorum. And we actually open sourced that as a generic, let's say, layer on top of, let's say, the Akka API in order to create actors just by executing RESTful calls. So it's basically a RESTful API shell on top of Akka to generate actors in a dynamic way. And what we actually use that for is that we have created a number of connectors, like and input and output actors, especially for Kafka as well as for APIs, in order to provide a dynamic streaming pipeline. The streaming pipeline is asynchronously connected to Cassandra, and in that way, actually, the model and the scoring are just loosely coupled. There is not a strong coupling between these two systems, which actually can be beneficial in some cases because then the two systems are actually kind of uncorrelated with each other, and they can have their own development, deployment strategies, and so forth. This project is actually open source, as I said, and it's on GitHub. And I would like to thank the guys that helped contribute in this project, and I'm very honored to be here and representing the entire project, as well as many other initiatives which are present at ING, and it's really so exciting to be at ING right now with all these, let's say, groups of data scientists and data engineers experimenting with technologies like Spark and Python and so forth. It's really a great experience. To conclude, this is the recipe that we applied, Spark, Cassandra, and Akka. Actually, in view of the time, I'll have to stop here, but there is a webinar on O'Reilly for the 9th of December, which will be like an extended version of 1 hour, and I'll probably be able to run some of the algorithms in Spark and actually start up the Akka pipeline so that you can actually see in working. And a bit of a feedback for the community. So I do believe that Spark is actually growing tremendously, and it's such a fantastic project where engineering and data science is coming together. I do think that there is still quite some more work that can be done and more projects that can be added in terms of machine learning. So algorithms which are common in R or Python, like DBScan, optics, PAM, or for instance, more metrics, more sort of space transforms, etc. As well as maybe non-distributed algorithms, which are still pretty valid in some cases. It would be great if more of these would come together and kind of thrive in the community and make Spark bigger and better with respect to the machine learning solutions. And another one, which is a bit of something which I'm just dropping here, but I think it's interesting, is we do need indeed Spark and Akka because we want to cover, let's say, millions of events as well as millisecond response. Is that an opportunity there maybe to unify also in that direction? Just humbly putting the question there. And Spark as a batch solution together with event streaming. Is there another way to maybe have another layer of unification in our APIs? That said, I would like to thank you all for being here, and also take the opportunity to thank ING for the vision and the attention that is given to data-driven strategies and the tremendous work done by our CIO, Peter Jacobs, and Henk Kolk, Chief Architect, in order to bring more, let's say, event-driven and data-driven strategies as part of bank processes. And of course, the communities of Spark, Cassandra, and Akka. Thank you for your time. Thank you.
Great, we can take one question if someone has a question.
You were saying that you were scoring models in Akka while training them in Spark. So the question is, how did you transfer the models from Spark to get them into Akka for them to be evaluated?
Yes, the question is whether how do you exchange models between Akka and Spark? Well, the best way to do it at the moment is actually by convention. So simply saying, okay, if we believe that a certain model has to pass over, and actually, you know, the problem is less severe now because part of the pipeline is still can still be developed in Scala functions, and those Scala functions actually can be taken over and moved to the Akka part. So it's not that we are actually dealing with two completely different frameworks which cannot exchange, let's say, modeling or code at all. So I would say, yes, there are ways to do so, and definitely using Scala as a uniform programming language does help.
Awesome. Let's give Natalino another big hand.
Thank you. Thank you.
Thank you, everyone, for coming. So some quick logistics.